A planet has half the mass and half the radius of the Earth. What is the gravitational field strength of the surface of the planet? The gravitational field strength at the surface of the Earth is G. The formula for gravitational field strength is Gm over r squared. And this is what it is on Earth. The second planet, the second planet has mass 2, which is half of the mass of the Earth. And the second planet, which is R2, has half of the radius of the Earth. So let's plug this in. G is equal to G, half the mass, times half r squared. So Gm over 2, and that's 1 over quarter, so we take the 4 up there, r squared. So it's 2Gm over r squared. So the gravitational field strength on the second planet is twice that on Earth, so we're looking at 20, 5D. Okay, question 6 is a longer question and it's in 2 parts. Part 1 is about kinematics and gravitation, and part 2 is about radioactivity. Let's do part 1 together. Part 1. A ball is released near the surface of the moon at time equals t equals 0. The point of release is on a straight line between the centre of the Earth and the centre of the moon. So let's say the moon is here and the Earth is there. The ball is here and it's being released back down to the moon. And that's the Earth. And this is a straight line between the two. The graph below shows the variation with time t of the displacement s of the ball from the point of release. State the significance of the negative values of s. Well, s is displacement, which is a vector. And you'll know from your topic 2 tutorial that whenever you do a question that has Suvat equations involved or acceleration in a straight line, you choose a direction to be positive, usually upwards, and then the other direction is negative. So anything that goes in the positive direction, we give a positive number, and anything that goes in the negative direction, we give a negative number. So for this answer, we'll write it down underneath here, the direction towards the moon is chosen to be negative. Therefore, a ball falling towards the moon will have negative displacement. Use the graph to estimate the velocity of the ball at time equals t equals 0.8. I'm going to get my ruler for this. So we want to go to 0.8, so that's 0.6, 0.7.8 there. And we want to draw a tangent to the line at that point. Let's move the graph down a bit. So it's not easy on an iPad actually, but we'll try anyway. So we've drawn the tangent to the line there. And why am I drawing a tangent to the line? Well, velocity is equal to the rate of change of displacement. So that means it's the gradient of a displacement time graph. So we want to find out what the gradient of this tangent is. So we're going to draw a big triangle, as big as we possibly can, because that reduces the error on the final mark. Our delta y is equal to, let's go to there, minus 2.35, and our delta x is equal to 2.25. So let's go up a little bit. V is equal to the value of the gradient, so it's delta y over delta x, so it's minus 2.35 divided by, oh, it's not 2.35 because it doesn't go from 0, it's oh my goodness, what is it? It's 2.85. Every time I touch the screen, there we are. 2.85 divided by 2.25 gives us an answer of 1.266. So that gives us 1.3 meters per second. So our answer is 1.3 meters per second. Second question of 6b says calculate a value for the acceleration of freefall close to the surface of the moon. So acceleration is v minus u over t. Let's just say we've got t is equal to 0.8 seconds. V is equal to 1.3 at that stage, we just worked that out. U is equal to 0 because it's dropped from rest. So we have 1.3 minus 0 divided by 0.8 gives us acceleration of 1.6 meters per second squared. There we are. What's next? I'm going to just note down the data we've got here. 1.6 meters per second squared on the moon. Okay. The following data are available. Mass of the ball, mean radius of the moon, mean orbital radius of the moon about the centre of the Earth, and the mass of the Earth. So we've got all those things available to us. Show that the Earth has no significant effect on the acceleration of the ball. Well, let's use G is equal to G over R squared, because that will let us find out what the gravitational field strength is. And let's find out what G is of the Earth on the moon's surface. So let's use this G is equal to GM over R squared with this distance here to find out what G is relative to the Earth at that stage. So G is Newton's gravitational constant, and you can look up the data booklet for that. It's 6.67 times 10 to the 11. M is the mass of the Earth, which is 5.97 times 10 to the 24. And R. Now R is this distance here. It's the distance from the centre of the Earth to the surface of the moon. So we know that the orbital radius of the moon about the centre of the Earth is this. But we need to subtract the radius of the moon here. We need to subtract that because we're talking about the surface of the moon. So we've got the mean radius of the Earth. Let's take that away. Let's do a quick sum. So our radius is 3.82 times 10 to the 8. So let's pop this back into the sum here. Squared. And the answer for this is 2.7 times 10 to the minus 3 meters per second squared. That's quite small. And if we remember from the previous question, let's just circle up here, our acceleration on the surface of the moon was 1.6. So this is the effect here of the acceleration due to the Earth, and this is the effect here of the acceleration due to the moon. And actually, it's a very small percentage of it, 2.73 times 10 to the minus 3 divided by 1.6. It's the equivalent of 0.2%. So the strength of the Earth's gravitational field on the ball is just 2.2% of what is being provided by the moon. So it is insignificant. What would be significant? A couple of percent. Anything more than 1% would be significant, but 0.2% is insignificant. Move on to D. Calculate the speed of an identical ball when it falls 3 metres from rest close to the surface of the Earth. So we're going to use a Suvac equation for that. It's going to fall 3 metres, and earlier we said that anything going towards the Earth was positive. So if that's the Earth and it's going towards the Earth, it's going to be positive. Right, if from rest, so u is equal to 0, v we want to find out, and a on the surface of the Earth is 9.81 metres per second. So v squared equals u squared plus 2as. V squared equals 0 plus 2 times 9.81 times 3. So v is equal to square root of that sum. .7 metres per second. Sketch on the graph the variation with time t of the displacement s from the point of release of the ball when the ball is dropped close to the surface of the Earth. Okay, and for this sketch, take the direction towards the Earth as being negative. So we want to draw a similar sketch of what the ball's trajectory is, but for the Earth. We know that after when S, and it's an ST graph, isn't it? So that's S and that's T. We know that at 3 metres, it's going to have a velocity of 7.7 metres per second, but actually we want to know where it is at that time. So let's just do a quick sum. To find out how long that takes. So at 0.78 seconds, it has a displacement of 3 metres. Let's go up here. Three metres, 0.78, so that's 0.75. There. We know that it's 0 at 0, and we know it'll be a nice smooth trajectory. So we want to draw a nice smooth trajectory from 0 down through that point. That wasn't very good. Let's try again. Try again. Oh, better. Okay, smooth trajectory. There we go. Question 7, motion of a rocket. A rocket is moving away from a planet within the gravitational field of the planet. When the rocket is at position P, a distance of 1.3 times 10 to the 7 metres from the centre of the planet, the engine is switched off. So we've got a planet. That's position P. At P, the speed of the rocket is 4, so the initial speed is 4.38 times 10 to the 3 metres per second. And our distance, S, is equal to 1.3 times 10 to the 7. 60 seconds later, so time is equal to 60 seconds, it has a final speed, V, of 4.25 times 10 to the 3 metres per second. At a time of 60 seconds later, the rocket has reached position Q, we're calling that Q. The speed of the rocket is 4.25 times 10 to the 3. Air resistance is negligible. Outline with reference to the energy of the rocket why the speed of the rocket is changing between P and Q. So the speed has decreased. First of all, the energy of the closed system is constant. As the rocket moves away from the planet, the potential energy increases. Therefore, the kinetic energy decreases. This means the speed decreases also. Can you hear my neighbour's little kids screaming in the stairs? A little baby. She's very cute. Okay, 7b. Estimate the average gravitational field strength of the planet between P and Q. When you're asked to find the gravitational field strength, there are two ways you can do it. You can do it gm over r squared, or you can just remember that it's equal to acceleration. So you can do v minus u over t. And in this case, we're going to use the second, more simple equation. We had all the values earlier, didn't we? 4.38, 4.25, 60. That's v, that's it. Oh, wait a minute. I've done that round the wrong way. The initial, so it's the final speed was 4.25. The initial speed was 4.38 divided by 60 because it took 60 seconds for that to happen. That gives us a value of minus 2.1667 meters per second squared. Everything is given to three significant figures. 2.17 meters per second squared. Question 4. Planet X has mass m and radius r. Planet Y has mass 2m and radius 3r. That's just a jumble of numbers. Let's draw a little diagram. So planet X has mass m and radius r. Planet Y has mass 2m and radius 3r. The gravitational field strength at the surface of planet X is g. So g equals g, x equals g m over r squared. What is the gravitational field strength at the surface of planet Y in terms of g? Okay, so gy is equal to g m over r squared. But for y, we're not looking at mass, we're looking at 2 times the mass. So g 2m, and the radius is 3 times the radius, all squared. So we've got 2 over 9 g m over r squared. Gm over r squared, of course, is g. So our answer is gy equals 2 over 9g. And the answer is A. Question 5. The two arrows in the diagram show the gravitational field strength vectors at the position of a planet due to each of the two stars of equal mass m. Each star has a mass of 2 times 10 to the 30 kilograms. The planet is at a distance of 6 times 10 to the 11 from each star. So what we're aware of here is the planet up the top is experiencing a gravitational field strength from both stars, and it's equal in value because the masses are the same, the distance are the same, and the angles are the same. A. Show that the gravitational field strength at the position of the planet due to one of the stars is g equals 3.7 times 10 to the minus 4. So a very simple question for us. Small g, which is gravitational field strength, equals big G, which is Newton's gravitational constant, times the mass of the star times the distance squared, divided by the distance squared. So Newton's gravitational constant is 6.67 times 10 to the minus 11. The mass is 2 times 10 to the 30, divided by 6.0 times 10 to the 11, all squared, gives us a value of 3.71 times 10 to the minus 4 newtons per kilogram. And everything is given to two significant figures, so we bring that down to 3.7 times 10 to the minus 4 newtons per kilogram. B. Calculate the magnitude of the resultant gravitational field strength at the position of the planet. Let me just remind you what's happening to that planet. Here's the planet here. It has a gravitational field strength from star 1, and it has gravitational field strength from star 2. Gravitational field strength is a vector. That means when you add vectors together, or you get the resultant gravitational field strength, you have to add these vectors tip to tail. So instead of showing the diagram like we have there, we're going to take this all out, and we're going to put our gravitational field strength in respect of star 2 like this, because we're adding them tip to tail. And that's from star 1, that's 2. And the resultant vector is the resultant gravitational field strength. And the resultant vector is from the start of the journey to the end of the journey. So we want to know what the length of that vector is. How can we do it? If we look at the gravitational field strength solely due to star 1, then we're looking at the length of this vector here. And you can see what we have is a right angled triangle. We know that this is 34 degrees, so this must be 56 degrees. Therefore, we can find out the length of this, let's call it x, by using trigonometry. Sine 56 equals the opposite length of there, so it's x over the hypotenuse, and the length of this hypotenuse is 3.7 times 10 to the minus 4. So divided by 3.7 times 10 to the minus 4. That means the length of x is 3.7 times 10 to the minus 4 times sine 56, which gives us a value 3.05 times 10 to the minus 4 newtons per kilogram. That's only due to star 1. And what we know for star 2 is identical to star 1. So actually this length is identical to the original length. So the total gravitational field strength, G, and actually I've said total, I think we want to like resultant there, is 2 times 3.05 times 10 to the minus 4, which gives us a value of G equals 6.1 times 10 to the minus 4 newtons per kilogram. Question 6. On Mars, the gravitational field strength is about a quarter of that on Earth. Okay, so gravitational field strength on Mars is equal to a quarter of the gravitational field strength on Earth. The mass of the Earth is approximately 10 times that of Mars. Okay, so 10 times the mass of Mars is equal to the mass of the Earth. What is the ratio of the radius of the Earth over the radius of Mars? Well, what we do know to bring radius into this is that G equals gm over r squared. So that means the gravitational field strength on Mars is equal to G over the mass of Mars divided by the radius squared of Mars. Equally, we can say that GE is equal to GME over RE squared. GMM over RM squared is equal to a quarter of GE, which is GME over RE squared. We can cancel out these G's. We also know that MM over RM squared equals a quarter ME, but instead of ME we can write 10 MM from here over RE squared. That means we can cancel out the MM. So what we have is we have 1 over RM squared equals 10 over 4 over RE squared. Let's bring the RE up and over. So RE squared over RM squared equals 10 over 4. Then we square everything. So RE over RM, which is the ratio we're looking for, is equal to the square root of 10 over 4. Now, 10 over 4 is 2.5. The square root of 4 is 2. So it's got to be less than 2. And the square root of 1 is 1. So it's got to be between 1 and 2. So the answer is C. Question 7. Define gravitational field strength. That's a nice easy mark. Gravitational field strength is the gravitational force per unit mass for a small test mass. And what that test mass means is it doesn't have a gravitational field strength of its own, or it has a negligible gravitational field strength. A2. State the SI unit for gravitational field strength. The SI unit is newtons per kilogram. I actually think this question, the answer in the mark scheme for this is actually wrong, because I wouldn't say Newton is a fundamental SI unit. I would say that the Newton is a derived SI unit. So it's still an SI unit, I suppose. And if you take it further, then Newton is equal to kilogram, meters per second squared. And we've got the kilograms per kilogram there. So these cancel out. So you could say that the SI unit for gravitational field strength is meters per second squared, which is the acceleration units. But the mark scheme is looking for newtons per kilogram, so let's go with that. B1. A planet orbits the sun in a circular orbit. So we're looking at circular motion. We've got the sun here and the planet going around it with orbital period t and orbital radius r. The mass of the sun is m. Show that. And we have this big expression here that looks scary. It's not at all. What we need to remember is the force holding this planet in circular motion is a gravitational force. So the gravitational force is equal to the centripetal force. So gravitational force is from Newton's law of gravitation. It's gmm over r squared. And that is equal to the centripetal force that's acting on that planet, which is mv squared over r. So these two small m's cancel. And we haven't got t in there yet, but we do remember that v is the orbital speed, and that is the distance it travels divided by the time. And the distance it travels is 2 pi r, that's the circumference of this circle, divided by t. So instead of putting v in there, let's put 2 pi r over t. So we've got gm over r squared equals 2 pi r, all squared, over t squared r. Let's cancel one of those r's. And let's rearrange for t. So t squared equals 4 pi squared r cubed, because we're taking that extra r up to there, divided by gm, which means that t is equal to the square root of 4 pi squared r cubed over gm. This comes up again and again. I highly recommend you become comfortable with that derivation. 2. The Earth's orbit around the sun is almost circular with a radius of 1.5 times 10 to the 11 meters. Estimate the mass of the sun. We want to know what mass is. Right, okay, well, we've almost got everything. We've got radius, check, pi, 4, g, everything's there, apart from the time period. Okay, what's the time period of the Earth orbiting the sun? Well, it's 1 year. We can't put it into years, we have to have it in seconds. So it's 365.25, and that 0.25 accounts for the leap year every 4 years. Times 24, we're down to hours, times 60, we're down to minutes, times 60, which gives us a value of 3.16 times 10 to the 7 seconds. Let's pop all of that information into our formula above. So 3.16 times 10 to the 7 equals the square root of 4 pi squared times radius cubed, 1.5 times 10 to 11 all cubed, divided by 6.67 times 10 to the minus 11 m. Gosh, okay, let's square both sides. We've got 9.96 times 10 to the 14 equals 4 pi squared times 1.5 times 10 to the 11 cubed over 6.67 times 10 to the minus 11 m. Right, we're going to do some serious maths here. M equals 4 pi squared times 1.5 times 10 to the 11 cubed divided by 66425.3. Pop all the numbers in and you come out with the answer of 2 times 10 to the 30 kilograms. It is worth remembering that that is the mass of the sun, well, at least knowing the magnitude of it, because you don't really want to be working out the sun to 10 to the 3, which I just wrote down there a second ago. It's 10 to the 30. Question 8. The gravitational field strength at the surface of Earth is G. Another planet has double the radius of the Earth and the same density as Earth. What is the gravitational field strength at the surface of this planet? Another little diagram coming on. This is Earth. It's got a radius of r and a mass of m. this other planet, let's call it planet X, has double the radius, 2r. Hasn't said anything about the mass, but we know it's got the same density. So density equals mass over volume. Mass is equal to density times volume. Well, we can work out the volume of this sphere. Density 4 over 3 pi r cubed. That's the volume of a sphere. But r isn't just r, it's 2r. So the mass of this object, this planet X, is equal to density 4 over 3 pi 2r cubed, which gives us density 4 over 3 pi 8r cubed. So the mass of X is actually 8 times the mass of the Earth. So it's 8 times 8m. Okay, so the gravitational field strength at the surface of this planet is G equals G 8m over 2r squared, which is G 8m over 4r squared. 8 over 4 is 2, so it's 2 times the gravitational field strength on Earth. The answer is C. Question 9. A satellite X of mass m orbits the Earth with a period t. So we've got the Earth here, satellite's orbiting, it's a radius r, it's got mass and time period. What will be the orbital period of satellite Y of mass 2m occupying the same orbit as X? So we've got another satellite Y. It has a mass of 2m but the same orbit, so the same radius. For this we want to look at Kepler's third law, and we actually derived a version of it in the previous question. It is this. That's Kepler's third law, and what it says is that the square of the time period is directly proportional to the cube of the radius. This m here is the mass of the central mass, which in this case would be the Earth. You can see it's not dependent on the mass of the object itself. It's not dependent on the mass of the satellite. So it doesn't matter if this is 2m or m. As long as the radius of the orbit is the same, then the period will be the same. So question 9b. Question 10. A satellite powered by solar cells is directed towards the Sun in a polar orbit around the Earth. The satellite is orbiting the Earth at a distance of 6,600 kilometres from the centre of the Earth. Determine the orbital period for the satellite, and we have the mass of the Earth as 6 times 10 to the 24. Let's write everything down. We've got r equals 6.6 times 10 to the 6 metres. We've got the mass of the Earth, and that, by the way, is me just converting from kilometres to metres. We've got the mass of the Earth as 6.0 times 10 to 24 kilograms, and we want to find out what t is. Again, we're going to use our version of Kepler's third law. T squared equals 4 pi squared r cubed over g m, and we have the radius, we have the mass, everything else is a constant. So we pop all those numbers in, and actually we come up with t squared equals 283,60537.6 to give us a value of 5,325 seconds. Let's put it down to two significant figures. 5,300 seconds. Now, I have just blasé said, oh, this is the derivation of Kepler's third law, and wrote down this equation. This equation is not in the data booklet. I highly recommend you memorise it, or are super quick at going through the derivation that we talked about earlier, like this that I'm doing right now, okay? V is equal to 2 pi r over t. So we've got 4 pi squared r squared over t squared equals g m over r, and then cross multiply 4 pi squared r cubed equals gmt squared. So t squared equals 4 pi squared r cubed over gm. Either become very quick at deriving that or just memorise it. Question 11. Newton's law of gravitation, and then we have 4 things to select from. A is equivalent to Newton's second law of motion. Is that true? Well, Newton's law of gravitation is this. And Newton's second law is F equals ma, or if we want to be fancy, it's the rate of change of momentum with time. So they're not equivalent, it's not A. It explains the origin of gravitation. No, it doesn't explain the origin of gravitation. There's much more intricate and detailed physics needed to do that. It is used to make predictions. Yes, well, we can work out the force between planets and objects using that law. It's not valid in a vacuum. It's not that either. Newton's law of gravitation is a field. It doesn't need any particles for it to transfer through. So that's not true either. Our answer is C. Question 12. Ion thrust engines can power spacecraft. In this type of engine, ions are created in a chamber and expelled from the spacecraft. The spacecraft is in outer space when the propulsion system is turned on. The spacecraft starts from rest. On arrival at the planet, the spacecraft goes into orbit as it comes into the gravitational field of the planet. Outline what is meant by the gravitational field strength at a point. Oh, well, we've seen this already. Fabulous. The gravitational field strength at a point is the gravitational force per unit mass on a small test mass. And why is it important to have a test mass? Well, a test mass is one where the gravitational field strength felt by the test mass or created by the test mass is negligible. 2. Newton's law of gravitation applies to point masses. There we are. Suggest why the law can be applied to a satellite orbiting a spherical planet of uniform density. Aha, right, well, spherical planet of uniform density means that all the mass acts as though it's from the centre of the point. So that's where the mass of the planet comes from. This satellite, in comparison to the planet, is absolutely teeny tiny. Do you think that the gravitational field created by this satellite has any effect really on that of the planet? Well, no. So in which case we can call this a test mass. It's in orbit a distance of r away from the centre of the planet. Question 13. The moon Phobos moves around the planet Mars in a circular orbit. So we've got Mars here, Phobos going around it in a circular orbit. Outline the origin of the force that acts on Phobos. Well, the force that's causing it to move in a circular orbit, and hence the centripetal force on Phobos, is the gravitational force experienced by Phobos by Mars. What's the gravitational force of the planet Mars? 2. Outline why this force does no work on Phobos. Let's have a look up here. Phobos is moving in an orbit and it's moving like that. At any stage of this orbit, it's moving at a tangent to its path. And at the tangent to its path, if you go into the force at any time, you can see that the force is always perpendicular to its distance moved at that point. And work done is equal to Fs cos theta. F is the force applied to the object, S is the distance travelled, and cos theta helps us work out the component of force in the direction that the object is travelling. Well, in this case, Fs cos theta, and theta is 90. Now, cos theta is equal to 0. That means that the work done is equal to 0. So no work is done on Phobos because the force applied, and let's put i.e. gravitational force, is at 90 degrees to the direction travelled. B. The orbital period of motion of a moon orbiting a planet of mass m is given by, and this is the version of Kepler's third law that we've been looking at, where r is the average distance between the centre of the planet and the centre of the moon. Show that, so we want to show that k is equal to this value here. So let's go back to the very beginning. The centripetal force is equal to the gravitational force. mv squared over r equals g mm over r squared. Cancel out the top m's. V is equal to 2 pi r over t. So we got 4 pi squared r squared over t squared is equal to g m over r. And I previously cancelled out those but didn't do that explicitly. Okay, so 4 pi squared r cubed, we're cross multiplying now, equals g m t squared. R cubed over t squared equals g m over 4 pi squared. And what we're likening it to is km, so k must be equal to g over 4 pi squared. 2. The following data for the Mars-Phobos system and the Earth-Moon system are available. We've got the mass of the Earth, and we know that the Earth-Moon distance is 41 times the Mars-Phobos distance. Let's name these two systems. Let's name Mars-Phobos X and Earth-Moon Y. So Ry is the Earth-Moon distance, is 41 times Rx. Okay. And the orbital period of the moon is 86 times the orbital period of Phobos. So Ty is equal 86 Tx. And we know that r cubed over t squared is equal to km, and that's for the x system. And we also know the same for the y system. What we also know is that the k's are equal. That's equal to g over 4 pi, or the other way around, I can't remember. No, that's right, 4 pi squared, and so is that. What that means is, if we rearrange each of these equations 1 and 2 for k, we can make them equal to each other. So rx cubed over t squared x mx is equal to ry cubed over ty squared my. And now I think it's a good idea to make some substitutions, okay? So we have ty is equal to 86 tx. So let's write this out again, but instead of writing ty and ry, let's put the substitutions in. So tx squared mx equals, now ry is equal to 40, so 41 rx cubed over 86 ty squared my. Rx cubed over tx squared mx equals 68921, and that's 41 cubed. Rx cubed over 7396, and that's 86 squared ty squared my. And we can cancel out that, and that. What we then have is 1 over mx equals 9.319 over my. And this 9.319 is basically 68921 divided by 7396. And we want to find out what mx is, which is the mass of Mars. So let's cross multiply again. My equals 9.319 mx. So mx equals my divided by 9.319. My is the mass of the Earth. So we've got 5.97 times 10 to the 24 divided by 9.319. And that gives us 6.4 times 10 to the 23 kilograms. And that is our answer. That was hard for 2 marks. Gosh, if you can think of an easier way of doing it, please do let me know. But we got there in the end.